So, good afternoon, everyone. Now I want to introduce Torbjørn Lofterud. He is a consultant at, he is an information and security consultant at Cybercom, and he talks about credit card encryption failures and shows 3 different scenarios how you still can get onto the plain data even when there is some encryption tried to apply to protect them. So give him a warm applause.
All right, can you hear me? Oh, step back a little bit. So, my name is Torbjørn Lofterud. I work as an information security consultant at Cybercom Group in Sweden. I do mostly credit card information security. So I work with PCI DSS, which is a standardized framework for credit card security. As such, I'm what's known as a QSA, Qualified Security Assessor. That means that I do assessment of companies that handle credit card information. I'm also a PA QSA, which is similar but focuses on applications that handle cardholder information. So in many cases, when you have a company that processes credit card information, they choose to adopt an application that is pre-certified for handling cardholder information. And I can verify or assess an application that it is truly secure or does encryption and handling of cardholder information in a correct way. I also work as a PFI, that's PCI DSS forensic investigator. That means that when something actually happens, when something goes bad with a credit card installation or a credit card handling company, for instance, there's a breach at the merchant, I can go in and do an assessment of what actually happened and do a forensic investigation trying to figure out what's gone wrong. And in my work, I often run into bad cryptography or bad implementations of cryptography, so to speak. So my presentation here today is mainly on the encryption part of PCI DSS. So how do you encrypt cardholder information in the right way, and specifically how you shouldn't do it. So, I don't know how many of you are actually familiar with PCI DSS. PCI DSS is a standard for how to handle cardholder data information securely. That is credit card information, the information stored on your credit card and on the mag stripe of your credit card. So it was standardized in 2004, and it became mandatory during 2005. It's a joint project between MasterCard, Visa, American Express, Discover, and JCB. So before PCI DSS, they had different regulations for how to handle credit card information or credit card information security. And in many cases, they overlapped, and in some cases it didn't overlap. Sometimes they were contradictory, and in many cases there was problems fulfilling one piece of the regulation if you wanted to follow another piece of the regulation as well. So the current version is 2.0. It's been through a few iterations. The major changes to the standard has been with regards to wording in specific areas. It's a very, so to speak, mature framework from the perspective that it doesn't actually change very much. But it contains 12 chapters. Each of these chapters address different parts of the infrastructure or the security for the infrastructure. For instance, Chapter 1 handles networking and firewall security, and Chapter 6 is with regards to development. And the chapter that we're going to speak about today is Chapter 3, which is specific to storage of cardholder data. So I'm not really sure if you can see it from. I'll just step back a little bit. Chapter 3, storage of cardholder data. And specifically, point 3.4, which is the encryption and storage of cardholder data and how to store it securely. PCI DSS says it is mandatory. Sorry. I'll just stand here in front of the beamer and hopefully it's better. PCI DSS says that it's mandatory to store cardholder data securely. And by cardholder data, we mean basically the card number. So you're not allowed to store other parts of the data. I mean, you're not allowed to store actual copies of the track data on a magnetic stripe, and you're not allowed to store the card verification value that is printed on the back of the card. But you are allowed to store the card number and the expiry date and other type of information that surrounds that, for instance, the expiry date. So you're allowed to store it, but you have to encrypt it. So in order to store it securely, PCI DSS says it's mandatory to use one of these 4 techniques. You can use a one-way function or a one-way hash, that is SHA-1. You can use truncation, which is that you basically only store parts of the data. I'm sure you've seen this on credit card slips and stuff like that. They mask the number with asterisks or X or something like that. So you're allowed to store the first 6 digits and the last 4 digits. So we'll look at this a little bit later. They mention index tokens and pads, which is kind of a strange wording. All right, so I'll just turn this one off, perhaps. All right, is this better? Fantastic. All right, so we were talking about index tokens and pads. Index tokens and pads are basically just a tokenization technique. You replace the credit card number with something else. So you take a specific card number and you replace it with a token that replaces it. And then you have a token index where you can look up your credit card at a later time. Of course, you have to store the credit card so that you can look up the token later on. And you have to use strong cryptographic techniques to store that one as well. And it says you have to use strong cryptography with associated key management processes and procedures. So 3.4 specifies how the strong cryptography, what is, how should I say this? What constitutes strong cryptography? 3.5 and 3.6 address key management and key management procedures. So, what is then strong cryptography? I mean, it's a very, very broad subject, so to speak. Well, it says it's an industry-tested and accepted standard and algorithms for encryption. What does that mean? I mean, that's not very specific either. And for hashing, it's a recommended practice, but not a specific requirement that a salt be included. That's not very specific either. So from that perspective, you have to dig a little bit deeper in the glossary, for instance, and in the communications from the PCI Standards Council to assessors. And this is a bit of a problem, because as a merchant or as an application developer, you're not going to read monthly newsletter from PCI SSC. That is the standardization organization for the standard. You're going to read the standard. And you're going to try to interpret that standard into something that you want to use, or that is in line with what it is you're trying to do. This leads to quite a large number of homegrown crypto solutions. So, I mean, they read a standard, they read a glossary, perhaps, and the glossary says, you should use SSS, you should use RSA, you may use SHA-1. I think it also says El-Gamal and, well, AES, and a few other things. But it says absolutely nothing on how to use these standards. It says nothing about cryptography on modes, for instance. It says, there was a short notice about using salts when using SHA-1. It doesn't say anything about padding for RSA, for instance, which is very, very important. So it turns out that people do a lot of interesting stuff. And one of the reasons that they just doesn't use their standard cryptographic library is because they all think they have unique requirements. So every merchant out there has a unique requirement. Everybody has a unique requirement. And everybody thinks that the standard doesn't address their requirements. So we want to do this, and the standard doesn't actually explicitly say that we can't do it, therefore we should be able to do it. Other people say our bank required this. And my favorite one is it's the le, as they say in France. I don't know why, but France has a lot of really, really weird cryptographic solutions out there. And everybody keeps referring to it. It's required by law to have a funky cryptographic implementation. So they want to do something really strange, or they want to do something really smart, or they want to do something that they think is that they don't think actually is supported by the standard. So they choose to use a cryptographic implementation that is in line with the standard, so to speak, that they use the algorithms that the standard has appointed for them. So the standard says you should use RSA, the standard says you should use SHA-1, the standard says you should use triple DES or AES, and in fact they do, but they use it wrong. And this turns into serious problems. So for this threat analysis that I've done, we're going to look at 3 different examples. So the first one is hashing. So, and hashing algorithm is like MD5 or SHA-1. It's a one-way function. You throw something in, you get a pseudo-random number back, and it shouldn't be possible to reverse that mathematical process. The second one is triple DES in electronic codebook format. Nobody uses that, right? Nobody. And the third one is RSA encryption without randomized padding, or armoring, as it's called. And this is also really strange. Why would you roll your own RSA implementation? I mean, it's really, really weird. But people keep doing that anyway. And honestly, I have no idea why, but they keep doing it. I've seen all of these. So during my forensic investigations or doing assessments of applications or merchants, I've seen these examples. And the reason I'm holding this presentation is so that people should be aware that even if you follow the standard to the letter, you are at risk of being vulnerable. And when someone steals your data, someone is going to come in and seriously have a look at what you've built. And it's going to be a problem if you haven't done it right. Seriously a problem. So I created a sample database set. It's 3 databases containing 10,000 cards, 100,000 cards, and 1 million cards. The first data set with 10,000 cards represents a small merchant. So it's a small e-commerce merchant. He has 10,000 customers, or he has 10,000 entries in his database. So that would be like a medium-sized web shop or something like that. A somewhat larger merchant with 100,000 cards, that would represent a large e-commerce merchant, or perhaps a store owner that owns a small grocery store or something like that. A small restaurant, perhaps, might have 100,000 customers. And one database with 1 million cards in it. The database with 1 million cards in it would represent a large e-commerce merchant or a small payment service provider. So he would have a database where he has collected 1 million credit card numbers and stored them in his homegrown cryptographic solution. Credit card numbers has a very specific formula. The first 6 digits are what is called the INN, Issuer Identification Number. It used to be called the BIN, Bank Identification Number, but all issuers aren't banks. So it's the Issuer Identification Number. Our database consists of different banks, it's about 25 different banks, with a different distribution for their bins. So we have one large bank, Bank A here, who has like 25% of the population, and I modeled this on Sweden. So I'm from Sweden, so I model it after what the Swedish market looks like. So the first bank that we have has about 25% of the market. So he has a specific BIN or INN that are the 6 first digits of all of his customers. There might be sub-bins after that, but then we have like 2 more banks that, one more bank that has 14% of the population, 2 more banks that have 7% each, and 20 banks that shares 47% of the market. So each of these 3 databases has been created with this specific distribution of bank identification number or issuer identification numbers. So, attacking hashed pawns. In the latest communication, or in the latest version of the PCI DSS standard 2.0, it is actually specifically written in the standard that you are not allowed to store truncated pawn next to a hashed pawn. So the pawn is the credit card number, primary account number. So you are no longer allowed to store copies of a truncated version of the cardholder data next to a hashed copy of the cardholder data in the database. So who would do that? I mean, seriously, we're missing 6 digits. So if we want to do a brute force attack, we're going to brute force 6 digits. I mean, that's seriously easy. So, okay, so they actually figured that out. And they put it in the standard, you're not allowed to do this. So, well, that's obviously a step forward. And I've had this discussion with customers who want to store a hashed copy of the pawn and a truncated copy of the pawn next to each other in the database. Weird. Sorry. But sorry. All right, I think they sorted that out. So even if we don't have access to the truncated pawn, which make it dead simple to brute force it, it's still a partial known plain text attack. Most credit card numbers are 13 to 16 digits, 13 to 19 digits. Most of them are 16 digits. So from the perspective of brute forcing, something that is hashed with SHA-1, that is 19 characters long, I mean, it's not impossible, but it's certainly, I would say it's certainly difficult. But we know quite a lot about the information that has been hashed. For instance, we know that the first 6 digits are predictable. We know that the first 6 digits are the issuer identification number. And if you know something about the market that you're in, you know who the major banks are. And when you know who the major banks are, you also know what the major issuer identification numbers are. So if we look at our previous example here, we know that this specific INN has 25% of the market share. So for our database, we know that 25%, or roughly something thereabout, is going to start with these 6 digits. In my example here, all of my issuer identification numbers start with the number 9. That is fake. All real credit card numbers start with the number 4 or 5. But just to make it easier, or not to accidentally include some real cardholder information, I choose the number 9 here. So we know the first 6 digits, and we know that the last digit is a checksum. So that doesn't really leave many digits. So it's 10 to the power of 9. That is 1 billion combinations for each bank. And doing 1 billion SHA-1s That is not considered difficult. That is actually quite easy. So if we want to attack a database containing cardholder information, we can choose which bank to attack. So we can choose a specific bank and only brute force their cards or their customer cards, and thereby reducing the overhead or the computations needed down to about 1 billion SHA-1 computations. And that is definitely doable. So, what's the easiest way to do this? Well, turns out there are some seriously great tools for cracking out there. And John the Ripper is one of them. John the Ripper doesn't support out-of-the-box raw SHA-1 or raw MD5 for that matter either. But there are seriously good patches for it. And there's also patches for doing like distributed computations with John the Ripper, so you can distribute the load. So it's really, really good. There's also the thing about the file format. John the Ripper expects a very specific file format. It actually loads password files from Unix systems. So what we do is we're going to just take all the hashes and append a username or prepend a username. So we're just going to name it like card, colon, and a hash. And that loads perfectly well into to John the Ripper. John the Ripper has something called incremental mode. In incremental mode, it basically just walks through all possible combinations and tries to brute them one by one. It is possible to configure John the Ripper to only use numbers, which is what we want to do here. But there's a problem with the checksum. So it doesn't actually understand the checksum. We could, of course, patch John the Ripper if we wanted to, but we can also just create a small word list generation program that actually does create the checksum and lets us specify the INN. So I wrote a small C program that just generates all of the combinations for a specific issuer identification number and calculates the checksum and sends it into John the Ripper. And John is so nice, it takes it on the standard input, and you can load the databases right into John. It is amazing, the scalability of John the Ripper. It actually loaded a 1 million database, no problems at all. If you look at the numbers, I don't know if everybody can see it, but the 10,000 card database, it takes 8 minutes to crack per INN. So that is per bank that you are attacking. With John the Ripper, it takes about 8 minutes. And I'm not using a really fast machine. I did this on my laptop. So, I mean, if you have it like, if you load it into like Amazon or something, it's going to get way faster. It scales quite well. The 1 million database takes like 525 minutes per bank. And if you load a database with 1 million cards in it, and you attack the database, or attack the bank that has 25% of the market, that is 525 minutes to crack like 250,000 cards. That's, the yield of that is quite impressive. And I mean, you're going to be happy with that for a while. So, of course, I mean, we can speed this up. I mean, and you could probably have a better search algorithm. I mean, I don't think John the Ripper was written to load a database or a password file with 1 million entries. I mean, it just wasn't, they never thought anybody would do that. It's amazing that it actually does it. And so, a better search algorithm would probably be the best. You could probably integrate the checksum calculation into John the Ripper, into the incremental mode, and have it brute force even faster. So, for the first one, seriously guys, don't use hashing to protect cardholder information. It's just stupid. Why would you ever want to do that? I mean, it serves no purpose to do that. If you want to do it, make sure you choose a really, really, really slow algorithm. So if you want to slow this down, how much do you have to slow it down? I mean, slowing it down like 10,000 times isn't going to cut it. You want to slow it down like 100,000 times. So it has to be seriously, seriously, seriously slow. And at that point, you're probably starting to break your application. Your application probably doesn't work anymore in this mode. So if you have an application that is 100,000 times slower than it is now, it's probably going to be a problem for you. So it just doesn't compute. If you want to do this, if you want to have a hash of a credit card, please use a unique salt for each credit card number. But then we're back to square one. Why would you want to hash it? If you have the reason people hash them are because they want to have a search key. So they want to hash the card again and search the database and see if there's a match. And if you use a unique hash for each card, that is not going to work. So we're back to square one. There's no purpose in doing this. Never ever store hashed credit card information. There is no purpose. There's no way to do it securely. The third thing here is, if you have to do this, and you chose a global salt, which some people do, a global salt will make it more difficult for me to do the attack if I don't know the salt, because I have to brute force the salt as well. And if the salt is long enough, it's secure enough, it's not going to be possible to perform this attack. But PCI DSS doesn't say specifically that you have to secure your salt. So people who read the standard and they go like, let's see here, triple DES and key management. Ooh, key management, that sounds difficult. I think I'll go with hashing. Yeah, that sounds easy. Let's do that. So if you want to go with hashing, the only way to do it is to use a global salt that is secure. And then you're back in 3.5 and 3.6. You're going to have to do key management. And that's the reason why people chose SHA-1 to begin with, because they didn't want to do key management. So I see no purpose in it. I mean, it's just don't, okay? Oops, wrong button. That was hashing, and I'm sure you're going to run into it. I mean, you're going to see it sooner or later. If you ever do like cryptography with regards to credit card information, people are going to start talking about hashing because they think it's really great because there's very few requirements regarding it. Just have them stop there and go into like triple DES or AES instead. So, someone who chooses triple DES. We use the same INN distribution. We have basically the same database. So we have 3 databases containing 10,000 cards, 100,000 cards, and 1 million cards. We store them in the database. I have separated the 2 halves of the card here because it's easier to read. I don't know if you in the back can actually read this, but it's going to be larger in the next few slides. We also store a copy of the truncated pawn. And this is something we see quite often. The merchant or the vendor or the developer choose to have a copy of the truncated pawn for convenience. So they show it to the user or to the service desk or the help center so that the customer can identify his card. So you don't want to show him the encrypted card. You want to show him something. And perhaps you don't want to do the actual decryption routine. So you have a spare copy of the truncated card as well. And even if we can't actually find this in the database, even if they don't actually store it in the database, we often find it in log files. Because they do transaction logging, and PCI DSS says specifically you're not allowed to store clear text data in transaction logs. So what do? They simply truncate it and store it in the transaction log. So even if you can't actually find copies of the truncated pawn in the database, it's often available in the transaction logs or in application logs and stuff like that. So, ECB, electronic codebook format. Who uses that? I mean, seriously, guys, who does that? Well, turns out people do. I've seen this twice, actually, and it kind of freaks me out because everybody knows you shouldn't do that. I don't think you can actually see this, but we have this classic picture. This image is from, this image is from Wikipedia and tells you why you shouldn't use electronic codebook format. And the reason for that is because when you encrypt something, it will always end up in the same way. So if you have an image, in this case of a penguin, and you encrypt it in electronic codebook format, the outlines of the penguin is still visible in the encrypted image. I know that Linux had this problem initially in the CryptoLoop setup, so that's why the penguin is the typical example for this. I've seen this done twice, and both of these were Java implementations. I don't know if it's Java specific. It might be some kind of default setup for Java. I don't know. But both of these implementations were Java implementations, and they were using TripleDes in electronic codebook format. The heart of the problem is that TripleDes uses 64-bit blocks, and a 16-byte credit card number fits snugly into 2 specific blocks. So I exemplify this here. The first half and the second half. So the 16 bytes get divided into two separate blocks, and each half is encrypted separately and stored in the database. So if we look at the database example again, I have columns separated into 2 halves, and we also have the truncated pawn separated here. So, when we're attacking a database like this, what we are searching for are collisions. So, when you split the credit card number in 2 halves, first, the first half is going to be encrypted separately from the second half. You run into the problem of having collisions whenever a card ends in one of the issuer identification numbers. So whenever you have a credit card number that ends in something that another card begins with, you are going to have a collision. And it does require a quite large database for this to actually happen often enough for it to be usable. I would say that from the 1 million card database, we can find collisions for a few % of the cards. But that is still a far cry from being seriously good encryption, right? So in this example here, we have the encryption value 76B, 7617A, and so forth, being attached to the truncated version of 2 different pawns. If we overlap these two, we can see that for each of these 2, we can now deduce several digits from the data. One of them is only missing 2 digits, and the other one is missing 4 digits. So if we could actually find a collision for the other half as well, which is highly unlikely, perhaps if we went to 10 million cards or 50 million cards, we could find like a dual collision. But I'd say that's quite unlikely. But for at least one of these specifics, we're only lacking 2 digits. Two digits short. That is a far cry from 6 digits that we were missing from the beginning. So out of this database, we might be able to attack, well, let's say a few %. But in a database of 1 million cards, that's quite a lot of data anyhow. And also, as the merchant who actually have this happen, it's going to be very, very difficult for them to figure out which card has actually been attacked, because they're never actually going to figure out what actually happened. So, out of these 2 digits, how many valid cards are there? Well, first of all, we know it's not 07, because then it would have been a full match. But 07 is the checksum, or right, 7 is the checksum. And so we begin with like 100 combinations, or 99 if we remove 7. But if we use the Loon formula, which is for the checksum, there's actually only 10 combinations left. And of course, I mean, yeah, sure, there's 10 combinations. And we don't really know which one are the real credit card. But we can brute force it at our local friendly web shop if we want to. I mean, sure, it's easier to hack something else. But from the perspective of where we started, we had a database encrypted with like triple DES, and we thought everything was super secure and everything was really fine. And now suddenly it turns out that we're only missing like 2 digits, and it turns out that we can use the checksum to reduce that to like 10 cards. That is not good. So, from this perspective, don't use electronic codebook. I mean, seriously, don't. Nobody should. Some people do. I don't know. I'm not really sure why. Whenever you, if you ever see someone talking about using like triple DES for storing cardholder data, be really, really, really sure that they aren't using electronic codebook format. What you want to use is Shifter block chaining. Shifter block chaining solves the problem of the collision. You can also use a different algorithm. If you choose to use AES, you don't have the splitting problem. So AES uses larger block size, and then what happens is that a credit card number actually fits in an entire block, and you resolve the problem. I mean, you really want to use Shifter block chaining with AES as well, but it's not that much of a problem in that sense. Is it a question or a comment? Yeah, sure. Right. So his comment was, you need unique initialization vectors, and that is absolutely correct. What you want to do is you want to use a standard. So PKCS5, for instance, actually defines how to do this securely. So you don't want to download like the reference for triple DES or AES and start using that. You want to use something like seriously good, and you want to pick a standard, and you want to pick something that you know has been validated. And in most platforms today, application platforms today, actually has support for this. I mean, I'm sure that it's easy to do in Java. I'm sure it's easy to do in .NET. So, like, use the built-in standard stuff that comes with your platform. Rolling your own cryptography is a really, 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 really bad idea. So, the third one is RSA. And this one actually never got implemented. I caught it at the implementation stage. I said, like, whoa, guys, stop. So I'm actually seeing this in real life. I've only seen it on paper. But anyhow, you know how RSA works. You have a public key and you have a private key. And whatever you encrypt with the public key can only be decrypted with a private key and so forth. So we have a credit card number that has come into our application, and we want to encrypt it. And we want to use the RSA algorithm. So we generate a key pair, we take the private key and we stuff it in a safe, and we sync that safe in the C at some unknown location, and we feel super secure. But we can't really encrypt a credit card number using RSA because it's too short. RSA expects the input value to be equal to the size of the key. So as a developer, we realized that we're going to have to pad it. So what are we going to pad with? Well, 0 sounds good to me, so we just 0 pad it. Now we have a string that is of equal length or equal size to the key, and we can run it through RSA with the public key, and we end up with a crypto binary blob. And for convenience here, I've base64 encoded it, and we stuff it in our database. And our database looks quite similar to what we saw earlier. So we have our cryptographic entries here. I've truncated them as well for brevity. We have a copy of the truncated pawn. Because in this case, we really need the truncated pawn to be able to show the customer which card it is he is actually choosing. So you're in the store and you say, I want to go check out, and you have stored your card, and you say, like, I want to use this card because you have, like, remember me or something. In some cases, people don't have the truncated path. But again, we might find it somewhere else. Perhaps we find it in the access logs or in application logs or something similar to that. So, well, turns out that proper padding is not an option for RSA. I mean, it is hugely important. RSA is a deterministic encryption algorithm. It means that whatever you put into that algorithm with the public key is going to come out exactly the same every time. So if you don't pad it or use proper armoring, you're just using a fancy SHA-1 or a fancy hashing algorithm. So we can brute force that data. We can turn that into basically the same attack that we used against the SHA-1 cards. Adding a proper randomized padding is referred to as armoring. And armoring is an essential part of using RSA. I'm just going to take some more water. Sorry. Let's start again. So, armoring, or using a like seriously good RSA implementation or RSA library is hugely important. But then we're back again at the reason why people want to do this. They want the deterministic parts of RSA. They want to be able to encrypt it again and use it as a database key. So that's the reason why they weren't using proper padding. Or they were actually using zero padding, because they wanted deterministic properties. And the reason they didn't go with SHA-1 was that they thought that's super easy to crack. We're going to use something that's seriously hard to crack. We're going to go with RSA, and then we're going to like shortcut and we're going to mess it up. So, if we have access to the truncated pawn, it's going to be super simple to crack. And even if we don't actually have access to the truncated pawn, we're back at where we were left off with John the Ripper. It's a partial known plaintext attack. It's 13 to 19 digits. It's basically always 16 digits, or in most cases, at least where I come from. The first 6 digits are predictable, and the last digit is a checksum. So, again, 10 to the power of 9, 1 billion. Doing 1 billion RSA encryption operations is quite easy. It's not as easy as SHA-1, I believe, because SHA-1 is like seriously optimized for speed. But it's still easy enough that it can be done on my desktop or laptop computer. And one of the key points here is that it's probably easier for you to decrypt it or crack it than it's going to be for them to actually do it for real, because they're going to have the hassle of actually accessing the private key and stuff like that. Oops, wrong button again. So, from the perspective of using RSA, it's hugely important to use a standard and use a standard implementation and use it in the standard way as it was intended to be used. And there is a perfectly good standard for this, PKCS1. If you ever run into anyone who actually does this, make sure you use the standard. And the standard actually applies armoring, so it's randomized padding. And the problem with the randomized padding is that the output is not going to be deterministic, and sometimes that's what people want. Sometimes people want the deterministic properties of RSA. So, There's one more thing I wanted to talk about, and that is where do you actually do the encryption? So if you have an e-commerce site, it's probably built in something like the three-tier architecture. You have a web server, you have an application server, you have a database, and the database probably has some kind of storage. And PCI DSS doesn't specifically say where you should do encryption. So people choose the easy route and say, yeah, I'm going to use like file-level encryption on my database. So all of my database queries is going to go into this crypto container. And sure enough, yeah, that's going to protect you from someone running into your server room and stealing your hard drives. I mean, that's the threat assessment here, right? I mean, someone hacking into your database, they're going to have access to the unencrypted data. Someone hacking into your application server is going to have access to the SQL database and have access to the unencrypted data, and so forth. So, I mean, the only thing we're protecting against here is someone actually stealing the hard drives. Perhaps also, I mean, if we do the backups of the crypto container, perhaps we are protecting ourselves from someone actually stealing the backup tapes or something like that. A similar scenario is where people say, yeah, we're going to load this proprietary SQL module that we bought that actually does like seamless encryption for our SQL database. Oh, well, we're back to the same area here. What are we protecting ourselves against? Well, we're protecting ourselves against someone actually like stealing the database server or like perhaps hacking the database server. But if the database server has the keys, someone hacking the database server is going to have access to the memory, and in the memory there's going to be keys, and we can extract those keys and use it. So it kind of serves no purpose there either. And then, of course, we can put the encryption in the application server. Well, that at least, at that point, we actually at least know that someone stealing the database or hacking the database or being the database administrator is only going to have access to encrypted data. But at the same time, again, if they hack the application server, they're going to have access to the keys there. And we can't really put it into Apache, right? So we can't actually have it in our web server either. So it's a difficult problem. And I realize that is probably why PCI DSS doesn't address it. So PCI DSS says it should be secure, and it's up to you to secure it. But what I want you to remember here is that don't just take the easy route out and place it in the database or at the storage level. The preferred way, or probably the most secure way, is to do it in the application server. So if you do encryption in the application server, you can, at times, and if you want to, actually use a hardware cryptography module, for instance, in the application server, but you're still going to have to run into the problem of if someone actually has access to that application server, they are going to have access to the unencrypted data. So it's a bit of a conundrum anyhow, but please don't take the easy way out and just use like TrueCrypt on the database server. So, thank you very much. If you have a question, please step up to the microphone. If you want to contact me with regards to this or PCI DSS, please do so. If you have like PCI DSS related questions, please ask them now as well. And you can always mail me PCI DSS related question as well if you kind of need a second opinion or something like that.
Test? Okay. Can you go back one slide?
I'm sorry, I didn't catch your question.
Can you go back one slide?
Sure.
Isn't it best practice to encrypt on every layer?
Again?
Isn't it best practice to encrypt on every of these 4 layers?
Isn't it best practice to encrypt at every layer? The question was, isn't it best practice to encrypt at every layer? Well, there's actually no need to encrypt at every layer. I mean, if you do the encryption at the logical application layer, then you're going to write encrypted data to the database, and the database is going to write encrypted data to the hard drive. So it is going to be as secure as your keys are, and key management is one of the more difficult parts of PCI DSS.
You didn't mention the presentation layer at first, but if you, for example, use HTTPS to encrypt on this layer, then it doesn't help stealing hard disks.
I'm sorry, I don't hear the question.
If you encrypt in the presentation layer with SSL, then it doesn't help to if somebody steals the hard disk. That's why I think.
Do you hear the question?
Excuse me, is it possible to make a little bit of silence in the room? Like, stop talking at the back. Please?
All right, let's try again.
If you encrypt on the presentation layer with, for example, HTTPS, that doesn't prevent anybody from reading plain text keys on the storage level.
No. So, you always have to secure your keys. I mean, that is equally important to doing it right in other aspects as well. And this is also an underrepresented area with regards to PCI DSS. It doesn't actually address how to do it really, really right. So it just says you have to do it right, but it doesn't actually specify what right is. So, next question.
So you're completely correct about the brute force possibilities of credit card numbers. It might even be worse than you're hinting. You know, getting a computer to do a 10 to the 6 operation to brute force through all like the 6 missing characters within truncation is instantaneous. For the full billion, I don't know if you realize this, but with